This is for class 12. This is a question from your textbook, class 12. Class 12. This is a question from your textbook, but this is a conceptual question. Concept for this is for concept. The question is current carrying circular loop lies on a smooth horizontal plane can a uniform magnetic field be set up in such a manner that the loop turns around itself that is turns about the vertical axis. Now, this is a question, this is a conceptual question or concept, that is. So I have selected it. A current carrying circular loop lies in a smooth horizontal plane. Can a magnetic field be set up in such a manner that the loop turns around itself, that is, turn about the vertical axis? That is, it turns about the vertical axis. So here, a current carrying circular loop. That means it behaves as a magnetic dipole. And your magnetic dipole is equal to I into area. This is the magnetic dipole. So this is your magnetic dipole. Now, when this circular loop is placed in a uniform magnetic field, then there is a torque, and this torque is equal to vector product, cross product of magnetic moment and magnetic field. So here you see this is torque, that is equal to I A vector cross B vector. This will be your I A cross B vector. This is your torque. Now, current I A cross B. So here you see that the direction first, the direction of the magnetic dipole, the direction of the magnetic dipole is perpendicular to the current carrying loop. The direction of the magnetic dipole is perpendicular to the current carrying loop, which is this loop is in your horizontal plane. The loop is in your horizontal plane. So the direction of the magnetic field will be vertical. So the direction of the magnetic field. So the direction of the magnetic field. The direction of the magnetic field will be vertical. So your direction of the magnetic field will be vertical. Remember that the direction of the magnetic dipole is perpendicular to the current carrying loop, and the loop is in the horizontal plane, so the direction of the magnetic field will be vertical. Now but the torque, because it has to rotate about the vertical axis, so the direction of the torque is vertical direction, because it has to turn about the vertical axis. Since it has to turn about the vertical axis, so direction of the torque will be also vertical, and the direction of the magnetic field is also vertical. But we know that torque is equal to m cross b, so torque is perpendicular to both magnetic field and dipole moments. This torque is perpendicular to both m and b. So the direction of the torque is vertical, and at the same time the direction of the magnetic field also vertical. This is impossible. The direction that is, because why? Because here the torque must be perpendicular to this theory tells that the torque must be perpendicular to both m and b. The torque must be perpendicular to both magnetic moment and magnetic field. The torque must be perpendicular. So the torque and magnetic moment, they can't be in the same direction. So your torque and magnetic moment, the direction of torque and magnetic movement cannot be vertical. Because torque must be vertical. The direction of to rotate it in the vertical axis, to rotate the loop in the vertical axis, the torque must be in the vertical direction, and at the same time direction of the magnetic dipole is also in the vertical direction. But we know that torque here it is perpendicular to both m and b. So the direction of torque and m both in the same direction. This is impossible. So this cannot be vertical. So this is impossible. So your answer is, can a uniform magnetic field set up in such a manner that the loop turns around it? Your answer will be no. So your answer will be no. This is a good conceptual question. First of all, you remember that a current carrying loop, it is a magnetic dipole, and magnetic dipole is mi dot a, and the direction of this magnetic dipole is perpendicular to the current carrying loop. This perpendicular is current is in the horizontal plane, so direction of the magnetic dipole will be vertical, and the direction of the torque is vertical because it has to rotate in the vertical direction along the vertical axis, so its direction must be vertical. So both torque and magnetic moment at the same time, they can't be vertical, so this is impossible. So the answer is no. So now next concept question. And the next concept question is, A loop of irregular shape, question is, a loop of irregular shape, irregular shape, irregular shape carrying current, irregular shape carrying current is located in an external magnetic field, in an external magnetic field, in an external magnetic field. If the wire is flexible, if the wire is flexible, if the wire is flexible, why does it change to circular loop? Why does it change to a circular shape? Why does it change to a circular shape? A loop of irregular shape carrying current is located in an external magnetic field. If the loop is flexible, why does it change to a circular shape? You must remember that to become stable, a system always tries to attain minimum potential energy. So in this case, a current carrying loop is minimum, so it will try to attain its minimum potential energy. Potential energy U, that will be equal to minus mb cos theta. Your potential energy will be mb cos theta. The loop will try to attain this minimum potential energy. It is somewhat like when a dipole is placed in a electric field, we find that the potential energy U is equal to electric dipole moment minus dipole moment P E cos theta. And the electric field and the dipole, it tries to align itself in the direction of electric field, either parallel or anti-parallel. So I want to recollect you one thing that you have read in electric field, that when an electric dipole is placed in an external electric field, the two forces, that means your net force is zero. You have learnt about it that when an electric dipole is placed in an electric field, it is placed in an electric field, the net force is zero, and the electric field, it tries to align the dipole, electric dipole, either parallel or anti-parallel to the electric field. So same is the case in that your formula was minus Pe cos theta, potential energy, and same is the case here for magnetic dipole. It is mb cos theta, same is the case. So here this will try to align itself, this circular loop, this loop will try to align itself in the direction of the magnetic field. It will try to align itself in the direction of magnetic field, that is theta is equal to 0. It will try to align itself in the direction direction of magnetic field. It will try to align itself in the direction of magnetic field, that is theta is equal to 0. So your potential energy will be mb, and we know that magnetic dipole, that is equal to minus IAB. So here what happens, that to have minimum potential energy, the area must be maximum. For minimum potential energy, your area must be maximum. Because your magnetic field and current is a constant, so for minimum potential energy, your area must be maximum, and the circle has the maximum area. Circle has the maximum area. So the loop will form a circular loop. So it will form a circular loop. So this is for your class 12, and this is for your class 12. And your U is equal to minus dV cos theta. This is for your electric field. Now the next question for class 12, that is class 12, the next question is class 12. Straight wire carrying a current of 12 ampere A is bent into a semicircular arc of radius 2 centimeter consider the magnetic field B at the center of the arc A. What is the magnetic field due to the straight segment? That is, a straight wire carrying a current of 12 ampere is bent into a semicircular arc of radius 2 centimeter. Consider the magnetic field B at the center of the arc. What is the magnetic field due to the straight segment? Here the figure is like this. At the center B, and this is your radius R. What is the contribution? This 12 ampere current is flowing through it. The question it is asked, what is the contribution of this straight wire in this magnet at the center? Means at the center of this semicircle, your magnetic field is B, this is given to you. At the center, your magnetic field B, this is given to you. B, this is given to you. Now, here it has been asked that a current is flowing through this straight wire. So, what is the contribution of this straight wire? The current this straight wire, contribution of this straight wire for this magnetic field B, its contribution. Wants to know its contribution. So here, let us go to the Biot-Savart law. Biot-Savart law. This is your wire, this is your DL, and this is your magnetic field, DB. This is your magnetic field, and here this is your R. So here you see that in the formula it is dB. In the formula you find that what you find, dl cross r. You find dl cross r. In this Biot-Savart law you find that dl cross r. But here you see that you take a small element dl. Here you see that the dl and r, say you match with this figure. This is dl, this is magnetic field, and this is r. You match this with this figure, with Biot-Savart law. Here you see that dl and r in the same straight line. That means the angle between dl and r is 0. So sine 0 is equal to 0. So there is no magnetic field. So answer is there is no magnetic field. There is no magnetic field due to the straight segment. Due to the straight segment. There is no magnetic field due to the straight segment. So due to this straight segment. Now, if we consider for this small segment here, see R, all this. So dl cross R, all this dl will contribute to this magnetic field B. All this dl will contribute to the magnetic field D. And here, so for this semicircle, the magnetic field at B will be, for this semicircle, we know that for a circle, that is magnetic field at the center is mu naught I by 2r. We know this, mu naught I by 2r. So we will calculate the magnetic field at B will be half of this. So the magnetic field at this will be half of it, B by 2. Magnetic field at B will be half of it, and this will be the total contributions of all this dl, of all this. This will be the total contribution of all this dl, and its direction will be, see, dl cross r, dl cross r, dl cross r. So you are dl cross r. You see my finger, dl cross r. So the magnetic field will be into the plane of the paper. Your magnetic field will be magnetic field will be into the plane of the paper. Into the plane of the dl cross. That means you are tightening the screw. So direction will be perpendicular to the magnetic field, will be into the plane of the paper.